Okay, everybody, welcome back. Hope everyone had a good weekend. Um, any questions before I continue? Finally finish up this chapter 7. It's probably one of the longest chapters that we have, but there's a lot of information there. So anyway, any questions? If no questions, I'll finish up this chapter 7 and then I will then jump into 8, but before I jump into 8, I'm going to take you back to the website, and there is a additional chemical or a resource for you dealing with polarity that kind of would help you maybe to get a better grasp or a better understanding about polarity with respect to a bond. Okay. All right. Well, let me continue. We ended up on this page 37. Where we were looking at bonds and then be able to draw the particular a couple of things. One, the dipole arrow, okay, which is let me change the color here, which is denoted right here, okay, where the positive end. First of all, we have to look at the two atoms that are given. We have to determine who has a higher electronegativity, okay? Because that tells us in which direction the electrons are being pulled to. And so we use a periodic table and we use our reference point of fluorine, which is on the top right corner, okay? Because fluorine has the highest electronegativity value of all the atoms, okay? And so the trend goes from left to right, it increases, bottom to top, it increases. Now, in general, all of the halogens, all of the elements underneath fluorine, when we compare them with the other elements, they always win out. They always tend to have a higher electronegativity. And that's a good thing to kind of keep an eye out, because if you see a halogen bonded to another atom, the halogen 9 times out of 10 beats out with respect to electronegativity. So once we determine which direction we need to draw the arrow, then we go for it. Now, in this case, you have a fluorine. Well, you don't have to go any further. You don't have to look anything up because fluorine is the most electronegative. So we draw the arrow from left to right, where the pointed part of the arrow points toward the fluorine, and then the positive part of the arrow is on the carbon. We also write the partial negative. It's a lowercase delta. It tells us that because of the electron pull of the fluorine, in this case fluoride, that there is a partial negative. There's a lot more electron density around the fluoride than there is around carbon, resulting in a partial negative on fluoride, excuse me, and a partial positive on the carbon. Now, this is what we call a dipole, okay? Dipole meaning two poles, positive and negative, but more specifically, it is a permanent dipole. And it's permanent because the nature of the base with respect to the two elements that are bonded together, okay? We go to the next example where we have oxygen and hydrogen. Hydrogen is on the far left side of the periodic table, very low electronegativity compared to oxygen. So the arrow in this scenario goes from right to left, okay, with the partial positive on the hydrogen and a partial negative on the oxygen. Now, the way that bond was written, it can very readily be written the other way, where we got the hydrogen and the oxygen going in the direction, no problem. We just draw the arrow in the different direction. Okay, partial negative on the oxygen, partial positive. Okay, and then in this scenario, we got phosphorus and chloride. The fact that you got a halogen on there again tells you, okay, it's going to the halogen is going to win over with respect to the pull of the electron. So there's a dipole going toward the chloride with the partial negative on the chloride and the partial positive on the phosphorus. Now, all of these are a polar bonds. They are polar because the nature of the beast with respect to the two different elements, there is a permanent dipole. Okay, with that being the case, then depending on the structure of the molecule, which takes us back to the Lewis dot structures, we can then determine whether this the species or the compound is overall polar or non-polar. Okay, but we have to determine polarity of the bond to help us out. All right, so with that, we move on. And of course, noble gases, they're inert, nothing's going to happen to them, with respect to any type of chemistry, and at least with respect to here at Chem 130. All right, these noble gases, they're much bigger, things can happen because those electrons on the outermost shell are held on loosely, so things can happen. But for Chem 130, all the noble gases are totally inert, nothing's going to happen. They are inert because they have that octet full, okay? That's the driving force in any chemical bond, be it ionic bond, be it covalent bond, is to get that octet around itself, because that is the most stable state that an element can exist. And that is true for the atoms. They're atoms themselves. There's a question as to, in the exam, why is this, let's say, sulfur stable in its state? Well, it's not really very stable in the elemental form because, one, it's a nonmetal. Two, it has only 6 valence electrons, okay? So it is driving, its nature wants to get into a more stable state. So in that scenario, the sulfur will want to gain 2 electrons someplace and become sulfide, and to maintain that octet around its valence shell. Okay, trying to get to the octet, that's the driving force. Here, you're being asked to add the delta notation in the polarity arrow. Okay, so what we do is you look up carbon and oxygen on the periodic table, determine who has the higher electronegativity by its position relative to fluorine. And, there are specific electronegativity values, but we don't need to sit and memorize them because we just use our benchmark of fluorine. So in this case, oxygen is a lot more electronegative. So therefore, the arrow will point toward the oxygen, resulting in a dipole bond with the partial negative on the oxygen and the partial positive on the carbons. Now, don't mistake this partial charge with the ionic bonds to have a full charge, okay? There's a big difference here, okay? Because if we look at sodium chloride, sodium ion has a full positive charge on it, and the chloride has a full negative charge. They come together because of the attraction of the positive and the negative. They have this electrostatic attraction, like two magnets coming together and holding on to each other by attraction. There is no sharing of the bond like the covalent bonds that we're talking about here, okay? But because of the electronegativity in that particular shared bond, there's an unequal sharing. And if there's an equal sharing, meaning that the electronegativity of both these species is the same, we have a nonpolar bond. If there's an unequal sharing, we end up with a partial negative and a partial positive, which is a polar bond, okay? And to determine which direction that arrow goes, then we determine those two elements, where they are in the periodic table relative to fluorine, and see who beats out. In this case, oxygen beats out. And so we draw the arrow from left to right. The next example, you don't have to look up anything because you got fluoride right there. Fluoride, it always wins. There's no question there. It will have the arrow going from left to right. Now, everything's written carbon, oxygen, but it can very easily be inverted. It's the same thing. It's just the arrows being written in the other direction, okay? Then we have oxygen, hydrogen. So in this case, the arrow goes from right to left with a partial on the oxygen. Then we got a carbon chloride bond with, again, it's a halogen. And just being a halogen in itself is enough to tell you, all right, we have electronegativity going from right to left in this scenario. Now, recall that the carbon-hydrogen bond with respect to electronegativity was essentially the same. And therefore, there's no dipole. The difference between the two is very, very small, negligible. So we treat that as a nonpolar bond, and therefore there's equal sharing, and therefore no arrow, okay? No arrow involved. All right, so in this set of questions, they're asking you, okay, are these bonds ionic? All right, and if not, they must be covalent. Obviously, if they're not ionic, they got to be covalent. And if they are covalent, are they polar or non-polar or equations, right? So the first one should be very easy to determine, because to be an ionic bond, what is your criteria for being an ionic bond? Do you recall? I mean, how do I look at a bond between two elements and say, oh, this is an ionic bond? What is the criteria for an ionic bond? And while you're there thinking about it, what's the criteria for a covalent bond? Exactly, Erica. The criteria for an ionic bond is a combination of a metal and a non-metal. And if you don't know who the metal is, again, that stair step on the periodic table, to the left of the stair step are the metals except hydrogen, which is a non-metal, and to the right of the stair step is the non-metal, okay? And so what we got to do here is look for a metal combination, metal, non-metal combination, okay? Which is sodium chloride. So sodium chloride is an ionic bond. Okay. Now, that implies that everybody else must be covalent. Must be covalent, right? Everybody agree on that? It's a combination of metal, non-metal. Now, question is, how do I determine whether this is ionic? We agree on that, okay? So everybody else must be covalent. Now the question is, how do I determine whether it's polar versus non-polar? What did I give you that you can at an instant determine just by looking at the two different elements involved in that bond for covalent bond? What can I use to determine whether it's covalent, it is polar or non-polar? Okay. Okay, let's look at this one. Bromine and bromine bonded. How do I know whether that is a polar bond or a non-polar bond just by inspection of that? Remember the general formula I use, AA versus AB? Remember that? AA bonded versus AB. You recall what I said about that? With that information, can you tell me what the BR-BR bond is? Is it a polar or a non-polar bond? Which is important to recognize, because that's going to determine it's a non-polar. Exactly, Jessica. nonpolar bond. Whenever you have two species that are the same, in this case, you got bromine, you got a nonpolar bond. What was the other example or exception where you have different elements that still made it a nonpolar bond? We just talked about it right there. Okay. Exactly. All right. All right. What? No, not exactly repelling. Remember, there's no repelling going on here. All right. Jessica, it's not quite like a magnet when we're talking about the covalent bond. What we're talking about here is in that bond, you're sharing these electrons. And because this fist on my left is a bromine and this on my right is a bromine, that sharing of electrons is equal. And so there's no tug of war going on, okay? Because both of them have the same electronegativity and that sharing is equal. Yes, there might be a little bit of a tug, but it's an equal tug. So it's a non-polar bond. Unlike a polar bond where straightforward, I got A and I got B, and one of these guys has a higher electronegativity, all right? Just the fact that they're different atoms tells you it's a polar bond, with the exception of the carbon hydrogen, okay? Of the carbon hydrogen. So that means that this is nonpolar, okay? This obviously the phosphorus and the fluoride's got to be polar, okay? Just simply by the fact that they're different atoms. We already identified sodium chloride as ionic, and we got the fluoride and the bromide bond definitely as a polar bond. Okay, that's all we're doing right now is just determine who's polar, who's nonpolar. And it's important that we know that bond, whether it's polar or nonpolar, because that could be one bond with a whole molecule. Then we take that information, once we determine all the type of bonds within the molecule, then we take that information with the Lewis dot structure and determine whether that molecule as a whole is polar or nonpolar. So we got two separate things that we have to grasp, okay? One, polar bond, nonpolar bond, just the bonds. Then we're going to work with that information coupled with the Lewis dot structure to determine whether the whole molecule is polar or nonpolar, which then that information tells us more physical properties concerning that molecule, okay? And we're going to be able to do a compare and contrast between two molecules of just by looking at their structure, looking at their polarity, determine who's going to have a higher boiling point, for example, a higher melting point, simply by knowing their polar bonds or whether a molecule overall is polar or nonpolar. All right, so let me clear this up a little bit here. And so we have nonpolar for the bromine, polar for the phosphorus fluoride bond. Sodium chloride is ionic, okay? And with respect, here's the thing that someone earlier mentioned about it, like two magnets. The two magnets analogy is for ionic bonds, okay? That's because they come together and they're full charge, full positive, full negative charge, and they are attracted to each other, analogous to a magnet attracted to each other. The covalent bonds are a little bit different, okay? They're sharing electrons, right? And one of them is going to be sharing the electrons or pulling the electrons more so onto itself than the other. And that results in a polar bond, and that's due to the electronegativity. We're going to go to the simulation software on your website to give you a better insight into the bond itself and what's happening here in a bit once we're done with this chapter. Okay, so the point here with polarity, it's a very important concept in chemistry with respect to a multiple thing. Okay, without polarity really allows us as chemists to synthesize and make all kinds of new compounds that without polarity, it would be very challenging to get reactions to react. Right? Not to say that nonpolar bonds cannot react, they can, but it takes a lot of vigorous conditions to get those things to react because lack of polarity. So, think of it as like stated here as a tug of war for bonded electrons. You're either going to have an equal tug of war, okay, or an unequal tug of war. When you have a unequal tug of war, you end up with a polar bond because that initiates a polar bond tells you that one of the atoms is pulling those electrons further onto itself because of the higher electronegativity of that element. Okay. But don't forget, carbon, hydrogen, always just definitely just think of it as nonpolar. Okay, very nonpolar. So here you have a list of compounds and you're being asked, okay, determine who is ionic, okay? And from after that, if once you determine if it's not ionic, it must be covalent. All right, if it's covalent, then is it polar or nonpolar? Is the question. So look at it this way, look at it like a flow chart. Okay, so we have the compound here, it's shorthanded. Okay, and so we determine it's ionic. Okay, and we know that because that is a metal, non-metal combination. Okay, metal, non-metal combination, ionic. So if we go the other direction, it is covalent. And we know that because this is a non-metal combination for covalent. Okay. Underneath the covalent, there's a subset, if you will, where it is polar, or you're just going to write NP for non-polar. They're both covalent. Okay, that's important to tell you. They're both covalent because it's a non-metal combination, but they're going to be polar because the electronegativity of one of them is greater. And so I use the analogy of the AB bond, where A and B are totally different elements. Okay. And for non-polar, I use the analogy of the AA bond, where AA is generic for they're the same. And included in there is the carbon hydrogen bond all the time, 100% non-polar. All right. So now we can know it's an AB scenario because it's different elements, automatically we're polar. Now the next question, once you know it's polar, in which direction does the arrow, dipole arrow go? That is dependent on which A or B is a lot more polar. Whoever is a lot more polar, that is the direction of the dipole arrow. And that results in a partial negative. And then the other side is a partial positive. Okay. All right. So in this scenario here, they're being asked who's ionic. Well, we can go quickly through that list. And we know ionic would be a metal, non-metal combination. Now, obviously, we've done sodium chloride before, good old-fashioned table saw. And then we got hydrogen chloride, which is non-metal. Hydrogen, which is non-metal. Chloride, carbon, non-metal. Carbon, hydrogen, non-metal. Okay, it's covalent. Oxygen, covalent. Hey, for potassium, oxygen, definitely ionic. Okay, so these two guys right here are ionic. And the phosphorus fluoride obviously is not ionic. It's also covalent. So everybody who's ever left here are now covalent. Now the question is, let's discern whether it's polar or non-polar. Well, we use the analogy of A bonded to A, meaning that whoever's bonded are the same elements, and incorporated in there is the carbon hydrogen bond, okay? Or we use the analogy of the AB where they're different elements, okay? Well, we got hydrogen and chloride. Well, that is an AB scenario, right? So definitely we got polar. here. We're not even being asked to draw the dipole arrow, but we will in a second. You know it's polar, okay? We got hydrogen and hydrogen, no question there. That's an AA scenario. So that would be nonpolar, NP. Chloride and carbon, got an AB scenario. So definitely a polar bond. Okay, here we're just looking at the bonds now. We're not looking at the whole molecule. We're just looking at the bonds. Then we got carbon hydrogen. That's this scenario. So definitely we have a nonpolar scenario. All right, so this would be an AA situation. And then oxygen and oxygen bond to each other, definitely another AA situation. So we got a nonpolar species. We already addressed carbon, potassium and oxygen. And then the last one, definitely a AB scenario. Okay, so we have a polar species. See how we went through it systematically? You know, we have a list, ionic, polar, nonpolar. Okay, let's find out the ionics, eliminate those because we know it is a metal, non-metal combination. Quickly did that. That means everybody left is covalent. All right, that's good. And from that covalent, we just draw on the AA general formula, if you will, to help me discern who's polar and nonpolar, keeping in mind that the carbon hydrogen bond, even though it's an AB situation, is really an AA situation because their respective electronegativities are relatively small. Difference that is small, so they consider it as the same. And then from that information, we're able to determine who's polar and who's nonpolar. Okay. Now, we can from there determine, okay, let's do the polar bond. So we have hydrogen and chloride, and we only need to do that for the polar species, right? So we just need to do that for HCl, and then for the chloride carbon, and then for the phosphorus and fluoride, because everybody else is nonpolar, so there's no dipole arrow, right? So here we got HCl. Find where they at on the periodic table relative to fluorine, and we'll find that hydrogen's way in the far left of the periodic table. So definitely chloride is the most electronegative, so it would have the arrow pointing toward the chloride, resulting in a partial negative on the chloride and a partial positive on the hydrogen. Okay. Again, the scenario here with carbon chloride, carbon is not as electronegative as the chloride. So our arrow in this scenario goes from right to left, where we end up with a partial positive on the carbon and a partial negative on the chloride. Okay. And then the phosphorus fluoride, no questions asked. You don't even have to look that up. The fluoride is the most electronegative. So definitely a partial negative on the fluoride, partial positive on the phosphorus. Okay. So we did all that. Okay. All that information in there. And all we did was realize we got this scenario, AB, AA scenario. Then we know ionic. It's definition of ionic, so we can discern that and get those, determine who they are. And then the rest are covalent bonds. And then given this AB scenario, we can determine who's polar and who's nonpolar. Okay. And that information is crucial, especially with covalent bonds, because once we identify the bonds of these species, and then we look at the geometry based on the Lewis dot structure, we can determine that whether a species is polar overall or non-polar. Okay. All right, clear up my mess here. Here you go. All right, so let's jump into molecular polarity for covalent molecules. Okay. When a molecule has all nonpolar bonds, that means that the molecule overall has a nonpolar molecule. An example would be CH4, methane. Okay, when we did the geometry, that's tetrahedral, and you ended up with something that looked like this. And I bring that out for a reason here. But the fact is that all the carbon-hydrogen bonds, there's 4 carbon-hydrogen bonds, they're all nonpolar, okay? Means that the molecule overall has a net nonpolar characteristic, okay? Now that tetrahedral configuration has symmetry. If you had a model of that, you could take it and you can kind of look down the plane and you can actually cut it down right down the middle and you have a left side and the right side, okay? So there's symmetry involved. So that what that means is just a whole area in chemistry dealing with symmetry. Whenever there is symmetry involved in the structure of the molecule, it can result in canceling out these dipole arrows, which means that overall the molecules can end up being nonpolar, even though they have polar bonds. So the geometry is very, very important. And this is what we mean by this. If we look at this species, sulfur dioxide, okay, and we compare it to this was, let me draw this out. This was sulfur dioxide, and this is carbon dioxide. Sulfur dioxide versus carbon dioxide. Now, in both cases, there are polar bonds, 2 polar bonds. What happens differently is this. If we remember, we did the Lewis dot structure for carbon dioxide, and we came up with this structure right here, okay? And it was a linear, it was an AB2 species, making it linear 180 degrees bond angle. Well, if we look at the carbon-oxygen bond on the right-hand side, and then we look at the carbon-oxygen bond on the left-hand side, the arrows go in opposite directions. Those arrows represent magnitude, okay, and direction. And they are what we call, we're called mathematics and things, vectors. In other words, it's a quantity that has magnitude, value, and it has direction. So, like, for example, if I only say 50 miles, and you're like, okay, what does that mean? Okay, 50 miles. But if I say 50 miles east, now you have direction and you have magnitude. Okay, those are called vectors. These are vectors, which means that these vectors, these arrows, they can cancel each other out visually. We can show it mathematically, but we're not going to go into doing that. And so if I have 2 arrows going in the same direction and they have the relative size and they're both worth 5 units, well, the total units here would be 10 units, okay? They're going in the same direction. Now, if I go put them in the opposite direction, same magnitude, okay, and I go 5 units in the positive direction, but because the one on the left is going in the left direction, that's a negative, that'll be negative 5 units. So negative 5 units plus positive 5 units equals to 0 overall net. And that's what's happening right here, okay, with the polar bonds between the carbon and oxygen. They are canceling each other out because of the geometry of the molecule. This results in the polar bonds canceling out. So overall, carbon dioxide is nonpolar, even though it has 2 polar bonds. Let me repeat that, okay? Even though carbon dioxide has 2 polar bonds, and those polar bonds cancel each other out, results in having a molecule that's overall nonpolar, okay? When we look at sulfur dioxide, when we do the Lewis dot structure on this, we end up with this A, B, 2, E. Well, point number 1, anytime there is a lone pair on the central atom, you don't have to go any further. You know automatically, I got a polar molecule, okay? That's like a little aid guideline to help you out. But if you don't recognize that, look at the arrows, okay? Unlike carbon dioxide where the arrows go in opposite direction, the left arrow kind of goes in the southwest direction, right? And the right arrow goes more like in the southeast direction. So they're not canceling each other out. There is still a net polarity. These vectors have a net value left over. So overall, since the polar bonds do not cancel each other out, we end up with a polar molecule. And if those lone pair were not there, we would have something like carbon dioxide, because what's happening, that lone pair there is causing that bond angle to be scrunched in, resulting in those bonds not canceling out. If the species was trigonoplanar, like something like this, the geometry, would be such that they will cancel each other out simply because of the geometry. Okay. This would end up into be a nonpolar species if I had a polar bond here, 3 polar bonds, but they would be nonpolar because they cancel each other out due to the geometry. But when we take out one of these guys out here and just put lone pair like sulfur dioxide, that crushes that angle. So now it loses its geometry and therefore ends up a nonpolar. Okay, so if you have polar bonds, the molecule, let me restate that. If you have polar bonds and the polar bonds do not cancel out each other, you end up with a polar molecule. If you have polar bonds and molecules do cancel out, the bonds cancel, the polar bonds cancel out, you have a nonpolar species. Let me give you another example of this polar species. I mentioned methane here, but you can have, we had this species here, but replace those hydrogens with 4 chlorides. And you had the same geometry, okay, as we did the methane, but a tetrahedral, and you end up with 4 polar bonds. However, because of the geometry of this tetrahedral configuration, those 4 polar bonds cancel each other out, resulting in a nonpolar molecule for carbon tetrachloride. This is what this species is. Now, if I replace one of those hydrogen, one of those chlorides with a hydrogen, now what's happened is I go back to a polar bond, because the 3 polar bonds don't cancel each other out. You got 1 nonpolar bond and 3 polar bonds. In fact, you got 1 nonpolar bond in the molecule, results in a polar species. Okay. All right. We talked about the tetrahedral, all of them carbon hydrogen bonds. If you see that example, they're asking you, okay, what's the polarity of that molecule? And if you put, all you see is carbon and hydrogen in that molecule, and by all means, it is definitely a nonpolar species. It could be something like this. All carbon hydrogen, okay? Nonpolar molecule, regardless of the geometry. Okay? We do PCl3. If you do the Lewis-Dot structure, and I'll let you do that, you should end up with this kind of a species, just like ammonia did, NH3. Okay, and we got 3 pairs of electrons all the way around the chlorides. Definitely polar bond. You got a lone pair in the central atom. Okay, and definitely makes it into a polar bond. Okay, and then we talked at length about carbon dioxide. We did that earlier. Where it's non-polar, so this guy is polar overall molecule. Okay, these up here are non-polar, and carbon dioxide is non-polar because the polar bonds canceled out. Yeah. We've done this already. We've done water, and definitely water and ammonia are very, very polar. Okay. All right. Well, that brings us to the end of chapter 7. What I want to do is to share, and I'll continue here with the next chapter in a minute. But before I do that, I want to share. Let's make sure I got the right one here. Okay, there we go. All right, on your course website, under the modules, there's a module listed as additional chemistry resources. We talked about build an atom. When we get into balancing equations, we can talk about this one, but click on the molecule polarity, okay? That should send you to this link here. Click on the link, and it sends you to the simulations. We're going to select the 2 atoms. You can go 3 atoms and then actually look at real molecules. We're going to do 2 atoms. Okay, we're going to do a couple of things here. Now, unfortunately, I wish they would change the letter A and B here, but make this right now because both of them have the same electronegativity. They're basically a nonpolar bond. Okay, and if we look at the electron density around it, the gray area represents the electron density, very uniform, equally shared. Why? Because the electronegativity in this scenario is both the same. So this could be an example of hydrogen. Hydrogen bonded to hydrogen, right? Where the electronegativity is essentially the same. Okay. All right, now let me clear this out. If I take the electronegativity of, let's say, B, I got a sliding bar here, and I increase its electronegativity, you can notice something. The dipole arrow starts to increase, okay? And the partial positive and the partial negative comes into play. Let me draw it this way. The red color represents a negative area, a high electronegative electron density. Okay, so it's picking up the partial negative. We got the arrow going on over here, okay? And I can just continue to increase. And if I increase that difference all the way through, notice what's happening is now it's more of that bond is more of an ionic character, where you have an example of a full negative and a full positive charge. But for covalent bonds, we're working with this scenario. Okay. Let me clear it up. And we can see that if we put an electric field around it, that dipole in the arrow is affected by non-electric plates. Okay. The partial negative areas attracted to the positive plate. Okay. And so here we have a dipole bond. Now, as the other negativity gets the same as the other one, then there's no dipole there. There's no effect, no effect on the, because there's no partial negative or partial positive side. The electric field has no effect on this molecule at all. Okay. So this is an example of a nonpolar species. Nonpolar species. So, play with this, you can see how that affects. So, and again, in this scenario, B has a higher electronegativity. B must be an atom that's closer to fluoride. So this could be an example of, let's say, hydrogen and chloride, okay, HCl. Anything where you have a covalent bond and you have a disparity of the dipole. Okay. So that's what that tool helps you out with. So hopefully you can see the difference. We use the color, we can use electron density. Notice how dark the partial negative gets because more electron density is involved there. Okay. Any questions? What I'm going to do is I'm going to jump in. We spent a lot of time on this chapter. Yeah, there's a lot of information there. So the next one is fairly short, and we'll be done with this one for sure next time. It won't take us what, three visits, I guess, 3 Zoom sessions. This one deals with nomenclature, okay, which is related to a couple things. One, nomenclature is basically the naming of the compound. It's a fancy word for name that compound. So you're given the formula, give it a name. You could be asked in a direction, give it a name, write the formula. Okay. Now, you will notice that in the periodic table that I keep sharing, that I have marked in red 16 elements that 100% of the time, metals, what their charge will be. We're going to be using the term called oxidation number. Okay. They're used the same, be it a charge, be it an oxidation number. We use a term oxidation number is more descriptive to identify both covalent bonds and ionic bonds. Because ionic bonds, as we talked about, has a full charge. So it's a full negative charge, full positive charge. Whereas covalent bonds, we don't have a full charge, we have a partial charge. And so the term oxidation number more represents everybody, be it covalent, be it ionic. Okay. So in group 1, which is starting with the metals, starting with lithium on down, those metals will always have a +1 charge. Okay, all the time, 100% of the time, no argument there. Okay, group 2, starting with beryllium straight down. Okay, those metals always 100% of the time have a +2 charge when they go from an atom to an ionic compound. Then on top of that, there's 4 more, which I list there. And that is aluminum, right here. Aluminum, we change a different color here. Okay. Aluminum, zinc, silver, and cadmium. Aluminum always has a +3 charge. Okay. And that's expected because, in fact, because it's in group 3. So always 100% of the time has a +3. Now the others are the B transition metal, the zinc, the silver, and the cadmium. Those 3, zinc always has a +2, silver always has a +1, and cadmium always has a +2. Okay, so the point being that there are 16 elements here that have 100% of the time a known oxidation number, aka charge, which means that when we name them, we don't have to do something special. That means that everybody else, all these other metals, what they have is a variable oxidation. Okay, all the other metals have a variable. And copper, for example, can either exist as a +1 or +2. So you see, it can be a little bit ambiguous. So what we do for those other ones that have a variable oxidation number, we use Roman numerals to describe them when we write their name out. So copper 2 could be copper written out as copper, parentheses, Roman numeral 2. Okay. And that tells us that we're talking about copper plus 2. Or it could be written out as copper, Roman numeral or parentheses, and parentheses, Roman numeral 1. Okay, that means we're dealing with copper plus 1. And that we only use that type of naming for all these other metals that can have a variable oxidation state. The ones in red, because they are like that 100%, we don't use Roman numerals. So as I mentioned earlier, we have sodium chloride. We simply call it sodium chloride. We know that sodium will have a +1 charge, so it's not necessary to put sodium or Roman numeral 1 chloride. In fact, it would be incorrect to include the Roman numeral for those 16, okay? For those 16. So, if you've not marked up your periodic table like that, you should, maybe, to help you remember that. +1, +2, and then the +3. And so the takeaway here, the ones in red, circled in red, do not use Roman numerals to describe their name in their name, okay? That means everybody else has a Roman numeral. So that's what we're going to talk about, sodium. Metals. Okay, so simple neutral atoms, we just call it sodium, is called sodium atom or neon atom, okay? We talked about knowing the names and the symbols for at least the first 20, okay? But on top of that, you want to use, add a Ba for barium, cobalt, next, iodine, copper, iron, lead, mercury, silver, gold, zinc, stannous, St. Yeah, its name could be stannous, but you may also use the name as kind of tin, Tin. Trouble with my pen here. Give me 1 second. This guy right here. Stannous or tin, Tin. So next time you're brushing your teeth, look at the label of the bottle. You might be brushing yourself with some stannous fluoride, which is tin, okay, ionic tin. And then strontium, nickel, chrome, manganese, and cadmium, okay? Which this is not the same as Mg, so check it out. Check out the name of that, Mn versus Mg. There's a difference there, okay? There's a difference. Another thing, K is not, when we say potassium, that's K. P is not potassium. P is phosphorus. Seen that a number of times. K is the symbol for potassium. All right, so make sure you get to know the symbols. Silver and gold get confused quite a bit as far as their symbol. All right, and let's see, that's about it, really. All right, and we're probably going to introduce a lot more of them as we proceed, but get familiar with these. We're going to start with these. All right, now with respect to naming for ionic compounds, and that's why it's important that we understand what an ionic compound is, the combination of the metal and the non-metal. Okay, for covalent bonds, again, it's a combination of nonmetals, okay, also known as molecular. Now, when we have the metals that are ionic, we have sodium. How do we know sodium has a +1 charge? Again, it's in group 1. Sodium element is in group 1. When it becomes ionic, it would lose 1 valence electron. Chlorides, all the halogens are in group 7. They're going to pick up an electron. Calcium's in group 2. It will end up with a +2 charge. They lost 2 electrons. Important. Metals lose electrons. Non-metals gain electrons. I've seen it written in some of the questions, the answers were that metals gain and lose electrons. But M130, that's not correct. Okay. Metals for us always 100% lose electrons. Non-metals always 100% gain electrons. Then we had the polyatomic ions. So be familiar with that table. Okay, let me refresh your memory. That table is on the periodic table, right here in the bottom left. Some of the most common polyatomic ions. We're going to be using those. The takeaway from that is that those polyatomic ions are units. Okay, units. And if we need more than one, we're going to put a parentheses around them and put a subscript for 2 plus. If we only need one, we just write it without the parentheses, just like it is. They have their specific name. Okay, we don't change the name. The NO3 negative charge is called nitrate. Plain and simple. We don't name it nitrogen trioxide or the sort. That's not its name. Okay, it's nitrate. And NO2 negative is nitrite, etc. All right, so be familiar with that polyatomic ions because we'll be using those. Okay, so as I stated earlier, I said we're going to be using the term oxidation number. And basically just a fancy name for the charge. And it's because we're dealing with partial charges or full charges of ionic versus covalent. So the oxidation state really symbolizes both scenarios, ionic or covalent. We all know now, hopefully, that all elements have a net oxidation number state of 0 because they have an equal number of positive protons and an equal number of negative electrons, okay, net 0. It is when they become ionic that now they change the oxidation number because they've lost or gained electrons. I talked about the fixed charge. Those are that sweet 16 on my periodic table. They have a fixed charge, so be familiar with those, okay, because when we start giving names for compounds that use the 16, we don't use Roman numerals, okay? All the other elements that are not part of the 16 with respect to metals will have a variable charge. The example of copper 1, copper 2, but you have things like iron 2, iron 3, and there's a variety of a lot more different ones. Cobalt has different ones. Lead can have different oxidation numbers, okay? We know now that metals lose electrons to become cations, and right, so we got to learn, refresh your memory on their respective charges based on what group they are. Important aspect of this is only pertains to those metals in the A elements, okay? We can predict that. The B elements, they're not as predictable, okay? And those are basically the 16. That means that all the other metals that are in there, other than the 16, can have an oxidation number state of a +1 all the way to a +9. It varies, it really does. Okay, now, so that means that those guys that have a variable oxidation number, we identify them by using the Roman numeral system. Okay, the Roman numeral. And this is where I think a lot of people are confused. So if you see it written out like iron Roman numeral 3, like written here, that tells you that Roman numeral belongs to that metal. And it's telling you that the oxidation state for that iron is +3, because iron can be in the +3 or it can be in the +2. Now, the old way of naming these things used to be ferric and ferrous, very ambiguous, very confusing at times. Okay, and so now everybody's agreed. The world, there's a organization called IUPAC, International Union of applied chemistry. So anyway, they've all agreed, they're the ones that say, agree on this is how we're gonna name things, so that the scientists in the other world knows exactly what I'm writing when I write something. I've been in the position where I've had a scientist from Japan, a scientist from Libya, where's the other gentleman? I forget what country he was from. Oh, Korea. So, and myself, we were in the lab trying to make a compound. Now, our respective native languages, our English altogether was, workable. But we sat there and we did all the chemistry on the board with just symbols and structures and so forth, and we were able to communicate. So chemistry can be a language of sorts in communicating. So we were able to communicate and design a way to synthesize a compound that we're trying to make. Okay, so the name is very specific, and how we name compounds and nomenclature. All right, we talked at length about nonmetals. They gain electrons, they can become anions. We talked about those in group 5. Nonmetals are going to pick up 3 electrons, group 6, 2 electrons, etc. Okay, we know about the noble gases, and the term happy, whatever that means. Stable should be a better term. I think I'm gonna go in there and get rid of happy throughout these things and replace it with stable. Okay, so naming compounds, ionic specifically, where we dealing with a metal-non-metal combination. We begin by learning the formulas and names for ionic compounds, and then we're going to move on to covalent compounds. Okay, remember that ionic compounds are made up of ions, and that ions have a charge. And then when we put them together, we have to have enough positives and enough negatives to cancel everybody out. We end up with a molecule with a net 0 charge. Okay? The polyatomic ions are found in the periodic table. Those are units. We don't separate them. If we need more, okay, for example, let's take the nitrate. If we need more than 1 nitrate, we will add a parentheses and maybe write a 3 subscript. That tells us we got 3 nitrates. And that's true for all of these polyatomic ions. If I need 2 hydroxides, I put a parentheses subscript 2. Okay, 2, so this is a good example would be calcium hydroxide. All right. And we don't change. In other words, I've seen, let's say you needed 3 nitrates for whatever reason. I've seen this happen, and that's totally incorrect. It is not 3 nitrogens and 9 oxygens. That is not nitrate. Okay. Now these are ionic compounds, and being ionic compounds, they're units. And one of the aspects about ionic compounds is this: when you put them in water to dissolve, they will dissociate into their respective units. And so if I had 3 nitrates in there, I were to dump them into a water solution, I would end up with 3 nitrate ions in solution of the water. Okay? They don't break apart. They stay together as a unit. So be familiar with these, keep those handy, you might need them. All right, so compounds, when we put them together, we're going to add enough cations and enough anions so they equal 0. So what we're going to do is first put them together to write the formula, and then we're going to talk about naming it, okay? So in this scenario, they're asking you to combine sodium and N for nitrogen. Well, we're not combining nitrogen, we are combining the ion of nitrogen, which is nitrite. The other aspect is this: remember, the anions their name gets changed. Okay, let me change. And so when we talk about nitrogen, that becomes nitride. Phosphorus becomes phosphide. Oxygen becomes oxide. Sulfur becomes sulfide. Fluorine becomes fluoride, chloride, bromide, iodide, IDE. Okay. And so remember those with respect to the names, because right now we're looking at sodium, combination of sodium and nitrogen. All right. So that means we have to realize what is the ionic form of both of them and the name. We know that sodium, the ionic form of sodium, is a +1. So I can quickly write a +1. I know that nitrogen, the ionic form of nitrogen, is a -3. How do I know that? Remember, it's in group 5. It's a non-metal. It's going to pick up 3 electrons because there's 5 valence electrons it has, nitrogen, and it's 3 to become more of a stable state and be isoelectronic with a noble gas in front of it, okay, which is neon. And so those are the ions. So we take the elements and put them into ionic form before we combine them. Then we look and we remember that we have to add enough cations and enough anions so they equal 0. So I have a -3 charge on nitride. That means I need 3 sodiums, okay? 3 sodiums to counter the -3 of the nitride. So that result, that 3 becomes a subscript for sodium. So the formula is Na subscript 3 and then N for nitrogen. The name becomes sodium. Okay, the metals, their name doesn't get changed. Sodium, whether it be an element or whether it be an ion, is sodium. It is the metal name. Sodium, and then we don't use Roman numerals, no Roman numerals. Why? They're part of the 16 that we know 100% of the time they're oxidation state. So hence Roman numerals are not necessary. Okay. In fact, they would be incorrect to use Roman numerals for these 16s. And then nitrogen becomes nitride. So the name for this molecule is sodium nitride. Okay. And we should be able to be comfortable with, given the formula, write the name, given the name, write the formula, work backwards. Okay. There's a tool that I study mate that in there you have 100 some odd combinations of different compounds that will aid you with respect to writing the formula and giving names. So you might want to use that to help you out. Okay. All right. So our formula for sodium nitride is Na3N. Okay. So here, let's do this. Let's go through the next step. They give you 2 elements, and then when you're okay, what are the? It's a metal, not metal, so we have ionic compounds. So what is the formula for this combination? Like we did before, we first put everything into ionic form, and we have sodium ion, which is +1. Okay, sulfur is in group 6. Therefore, in ionic form, it would have a -2 charge because it picked up, it's a nominal picking up 2 electrons. Furthermore, its name goes from sulfur to sulfide. Just like nitrogen went from nitrogen to nitride. Okay. Now we're going to put these 2 together. So I got sodium's a +1, sulfide's a -2. So I need 2 sodiums to counter the -2 of the sulfide. So its formula, that means that number here becomes a subscript for sodium. So I write sodium subscript S. It will be incorrect, and I kind of overemphasize this, to write it as Na like this. Okay, that is not correct. That is not the formula. It's a subscript. You got superscript, subscript, and coefficients. Okay, right now it's acting as a coefficient, telling us we need 2 sodiums, but that coefficient becomes the subscript in the formula. So that is a formula. The name now is sodium sulfide. Okay. Okay, let's look at this one. Magnesium, find it on the periodic table. Magnesium is group 2. Ionic form magnesium is Mg2. Oxygen, like sulfur, is in group 6. Okay. It has a -2 charge. In this scenario, we can put these together as a 1-to-1 because I got a +2 and a -2. They can come together as simply a 1-to-1. Okay. So the formula becomes MgO, and the name is magnesium. Oh, let me clear this up a little bit. We had sodium sulfide. This is magnesium oxide. Okay. Question here. Okay. Who could answer that question? How do we know magnesium is in +2? Good question. How do we know magnesium is +2? It's important. Okay. What group is magnesium? I'm sharing where's magnesium on the periodic table? First, we got to find it so we can answer that question, right? Who can tell me where magnesium is based on the table I'm sharing? It's an alkaline earth metal, that's correct. Can you tell me specifically where it's at? Yes, there we go. It has 2 valence electrons. Okay. It's right here. Okay, it's in group 2A. When it becomes ionic, it's going to lose those 2 valence electrons. Therefore, it will have a +2 charge. In fact, everybody in this group will have a +2. Everybody in this group will have a +1 charge. Okay, that's important to know now. And then the ones I circled here, aluminum will always have a +3. Okay, zinc and silver and cadmium, which are in the B metals, the transition metals, which have a variable, those 3 are the only ones other than the other ones that always have a constant oxidation number. Zinc +2, silver +1, cadmium +2, and aluminum. So there's 16 elements, that's important, 16 elements, metals specifically, that have a known oxidation number. And therefore, they would not use the Roman numerals to identify them. Okay. All right. Now, how do we know that sulfur had oxygen has oxygen? How do we know oxygen had -2 as a metal? Excuse me, as an ion. How do we know oxygen has a -2? What group is oxygen in? Well, first of all, it's a non-metal, right? It's a non-metal, and therefore it would gain electrons. And we need to know what group it's in because it's in group 6, which means there's only 6 valence electrons, and we're striving for that magical 8. Okay, and so oxygen will gain 2 because now it's full. It went to the magical 8, just needed 2. Hence, it will have a -2 charge. Okay. All right. Well, let me do this because I got 216 right now. I went over a little bit. Let me stop it here. And that would be 8 and 24. Okay. So what my recommendation is that one, you go back to the periodic table and you really identify the metals that you're going to know what kind of oxidation state they're going to have. Specifically, and grasp that, because we're going to be using those. The ones that are variable, you know, we don't need to know exactly what oxidation they will have. For example, I can give you this formula right here, which is copper. I want to explain what the name is, but that's the formula, copper chloride, okay? The question is, what is the oxidation state of copper? Well, we don't know what that is, but we can calculate it, right? Because we know the oxidation state of the chloride. Always a -1, and there's 2 of them. So it is copper plus a -2 is equal to 0. So we got copper minus 2 equals 0, because the sum of the 2 must equal 0. What must be the oxidation state of copper in this state right here? What is sulfur? Cu minus 2 equals 0. What must copper be? Copper must be a +2. Okay, so in this state, copper in ionic form must be a +2. The chlorides, there's 2 of them, are always a -1. So we calculated what oxidation state copper is in based on the partner. And sometimes we would know the cation and try to calculate the anion, or vice versa. We know the anion and calculate the cation. Okay, but more on that next time. Let me stop it here.